Another processing challenge which is very unique to the 3D nature of the FinFET device is these spacer strangers. So remember when we did our planar transistor process flow, we had these spacers around, our gate, and they helped us in defining these source drain extension and defining these source drain implant regions such that you get an extension and you get a much higher doping source drain implant. And they're also helpful when we were landing contacts to our device. So spacers are essentially an essential part of our transistor flow. But when you have a 3D device, so forming these spacers around your gate becomes very complicated. So let me demonstrate that using this 3D figure over here. So it's only, you can only understand it when you look at this in a 3D manner. If you're coming from a 2D frame of mind, it becomes very difficult to understand it. So I'll do my best to use this 3D figure to illustrate it. So the way these spacers are defined is you put a conformal layer and of your nitride around, and then you etch it off on the top, and you're left with these sidewall spacer. The problem or one of the challenge with this FinFET device is that you have multiple of these sidewalls. So you have this first sidewall which is from your gate, but you also have these other sidewalls which are from your fin. So you have these fin sidewalls as well, and each of them will form a spacer. How? So let's take a look at it. So if we defined a nitride around it and we etched it off from the top to make a spacer, so we'll get one spacer which is aligned like this way. So I'm looking along this plane. So I'll get let me draw it more carefully. So I'll get one spacer which is around here. So I'll get one spacer which is around wrapping around this vertical sidewall. So I'll get one of these spacers around here. So this is one of the spacers that I actually want. So this is my spacer wrapping around my gate, which I actually want to keep, but I also get this spacer along this vertical sidewall. So I'll also get a spacer if I draw, let's say this was my x-axis, and if I draw along the y-axis, so I'll get another of this spacer which is around my fin. So this becomes again I want to keep this particular spacer which is on my gate sidewall. So I want to keep this spacer, but I don't want this spacer around my fin. It prevents me from implanting this fin. It's also bad if I want to make a contact, because I can't make contact on the sidewalls because if they are covered with the spacer. So what I want is essentially I want to keep this first spacer which is on my gate sidewalls, but again I want to get rid of this spacer along my fin sidewall. So this complicates my process flow quite a bit, and it requires very special etches or very precision etch control to etch off this spacer on the side while keeping the spacer on my vertical sidewalls. So here I'm illustrating this same phenomena. So for illustrating it better, I have what I've done I've borrowed this figure from this paper, and they have illustrated this problem by taking these two cross sections. So what they have done is they have taken a cross section along this plane, which is the plane where I want to make a spacer. So I want to make a spacer around my gate sidewalls, and then they have taken a cross section along my fin, and I don't want to make a spacer along this sidewall. So the way I do it is I define my gate to be taller than my fin. So my gate is wrapping around, so it's much more taller. So this gate, the gate height is much higher than my fin height. So what I get is I get a spacer over here, and so I get a spacer which is wrapping around my gate, and I also get a spacer wrapping around my fin. But remember, my gate height is now much taller as compared to my fin height. Then what I do is I do a etching process. So I try to etch this spacer from the top. So I do this dry etch process, and I continue that process such that I remove this spacer on my fin sidewall. So I remove this spacer on my fin sidewall, but I'm still left with the spacer on my gate sidewall. So again, it requires a very precision, very good etch process to remove this stringer on your sidewalls, but to keep your spacer on your gate sidewalls. So this is again something very unique because a unique processing challenge which arises because you now have this 3D device. The third challenge which I want to touch upon in this video is related to forming of these source and drain junctions. So when we talked about planar devices, I described to you that how do we it becomes very hard to control these short channel effects, and we require these multiple of these implants. So we require a halo implant which is heavily dosed and of the same time as the substrate. We require a source drain extension implant to keep this depletion region from moving away into the channel. So how does that change in the context of this FinFET device? So as we go from this planar to this 3D structure, so how does that change? One of the advantages of going to this 3D device or this FinFET device that I've labored upon multiple times is that you get a much better gate control. So your gate is now wrapping around this thin fin, and shown here is this electric potential. So if you apply a voltage of, let's say, 1 volt here, your gate essentially prevents, since and you have 0 volt on your gate, this gate prevents your drain voltage from penetrating into your fin. And if you take a cross section along this direction, which is shown here, so your drain potential is pretty much contained in this drain region, and it does not penetrate through your fin to your source. So you get a much better gate control. So the point I want to repeat that is that since you have this much better gate control, it kind of helps your implant design a little bit. So what you can do is, if you have a much better gate control, you can what you can do is you can remove this halo implant. So you don't need this halo implant because you have good gate control. You can also probably eliminate the source drain extension implant as well if you are really smart, and you can contain your source drain, control the diffusion of this implant, which is your source drain, main source drain implant, very well, so that you produce a nice overlap. You can eliminate this source drain extension implant as well. So this is really good news, right? So I described you earlier that we had these multiple implants and how cool it was, but let me admit, I was really kidding. It's this implant in a planar device is really a mess, and to compete and to control these multiple implants in the diffusion, it was a real mess. So as compared to 3 implants, I'm managing just with one of these source drain implants in my FinFET device. So that's good news, and that should be pretty exciting. Another advantage that you get from moving to your FinFET device from a planar device is now you have an entire new way of defining your junction depth. So remember when we talked about junction, so we had this depth of our junction region, and Mr. Dinard in his scaling law for Dinard scaling had required us to scale this junction depth every generation by 0.7x, and we found that first of all it was really hard to do because we could not prevent the diffusion of this junction. Secondly, our doping was limited, so our resistance from our source drain was really going high. But in a FinFET device, we have an entire new definition of junction. So in a FinFET device, if you think about it, this is your source and drain. So your junction is essentially just defined by your fin width, or it's defined by this thickness of this silicon layer. So if I take a cross section of my device, if I cut my device along this direction, what it will look like is essentially you have your silicon fin, and you have these two gates around it. So this is the gate from this side, and this is the gate from this side, and my junction is essentially just this region which I defined in my fin, and this junction depth is just defined as my fin thickness. So this is this is an entirely new paradigm shift in the way we define junction depth. And but it's again it's something that should make me happy, because I can now control my junction depth just by controlling the depth or controlling the width of my fin. So why did I list this as a challenge? Look, there are two smiley faces here. So what's the problem? The problem is, again, it comes from the 3D nature of this device. So to define this, to make this source and drain region, what I need is I need a very uniform implant in my source and drain part of the fin. So the problems come from this effects called as which I'm calling here as shadowing. So what I need in my source and drain part of my fin, what I need is that now since my junction is this entire region, what I need is I need a constant uniform doping in this region, and to do that I need to essentially implant it along multiple directions, so that I get dopants from the top, I get dopants from the side. But what I need is essentially I want to create this I want to dope this entire fin with the same concentration of dopants, and that requires me to do this implant along this multiple angles. So this is where things start to become problematic. And what the problem that we get is you have these 3D nature of these fins. So you have these fins sticking out, and when you are implanting, so let's say these are the p-type fins. So when you are implanting your p-type fins, you want to cover your n-type fins, so you'll cover them with a resist, and there's only a limited amount of spacing that you are supposed to get between your p-type and n-type fins, and you have this resist. So the problem you encounter is that you cannot implant at very high angles. You can only implant at vertical angles, because if you implant at these high angles, most of your implants coming from here will be essentially shadowed by this resist. And that's the problem over here. So the problem comes from shadowing that you get because of this 3D nature of the device. And when you are trying to doing your implantation at a tilt, you can't get it into this fin, because that implantation is shadowed out by this resist. So the point I want to drive home, hopefully by describing these three challenges, is that the devil is really in the details. So we can draw these pretty and nice pictures of these devices, but when you get to the actual processing and you run through your process flow and you want to make these short channel FinFETs very close to each other, then you run into all these problems. And this is the upside to that. A positive side to look at it is that there'll be always these multiple problems, and it will require an army of engineers to process and integration engineers to solve them. So an upside to is that there'll be always jobs in this field.